about quantum mechanics, so it means we'll be able to go quickly through this. Alright, here we go. There are a couple students that made a PowerPoint they're going to send to me, so I can steal their good work and use it. I won't use it as my own, I'll give you credit, okay? I'll put your name in the bottom in black where you can't see it. No, I will give you credit. Quantum mechanics is really cool. For everyone that's learning about it first time through, there's some really amazing things. And for you that are learning about it the second time through, there might be some things that apply to chemistry that don't necessarily apply to physics. It does happen sometimes. So, the cool thing about quantum mechanics is it explains some things in the universe that are difficult to explain. The study of chemistry has sometimes been called the study of electrons around an atom. Chemists focus so much on the electron, and we know a lot about the electron. We know a lot about when electrons move from energy levels, energy is emitted as light. Can we determine the energy that is emitted by light when it moves from energy levels? Absolutely. When the energy goes in, the electron jumps up to a higher energy level. When it comes back down, the energy is released. The interesting thing about the energy definition for the atom, which is often the number one misunderstood concept, is when the electron is an infinite distance away from the nucleus. When it's an infinite distance away, this is defined as 0 on the energy. But the funny thing is, below this is below 0. So all of these values for energy levels are all negative. They just, when you say that it gains energy, it goes closer towards the 0. When it loses energy, okay, it loses energy. That energy is emitted as a photon of light or ultraviolet or infrared or different electromagnetic radiation. So that idea hopefully was shown very clearly in the last lecture. But Niels Bohr said that anyone who is not shocked by quantum theory has not understood it. So you're going to be shocked. You're going to understand it, and you're going to be shocked. So the cool thing about this is Niels Bohr model was the planetary model. The Bohr model was devised on shells, also called the shell model. You could find the energy of each shell or the energy level based on this calculation. If you have one electron, it worked great. It worked perfectly. The problem is, in every single other atom on the periodic table except hydrogen, there is not just one electron. So you've got an electron and another electron. What charge are on the electrons? Negative. So if they have negative charges, what do they do with one another? They have the ability to repel. They also have the ability to attract to the positive nucleus. So you have interactions between the electrons. So when you got one electron, Bohr's model works. When you got two, boop, done. Well, what about 3? No. What about 118? No. So we've got a little bit of a problem. Doesn't work. Energy, the calculations don't work. Now, that didn't stop Bohr from trying to understand what was happening with the atom, but unfortunately, it failed completely. Okay? No doubt about it. Now, he was completely successful, but he failed at everything except one. So, you imagine, okay, this is our quiz today. We've got, if you get 1 out of 115, you win. That's Bohr. Okay? It sounds like really bad, right? But the cool thing is, even though he didn't get the next model, mathematically it doesn't fit. So Bohr's model was a failure, just like all other models before him. Which we're learning, hey, what? No big deal. He still gets a model that most people understand about elements. Planetary model doesn't work. Okay? It only works for hydrogen atoms and other monoelectronic species. So if somehow you had lithium with only one electron, it could work. Doesn't usually happen very often. Electrons don't move in circular orbits. They do not move like planets. We know this based on measurements and data. The quantization of energy is correct, but because electrons are circling like planets, Okay, that's not why the quantization of energy is not correct because of planets. Okay, not because of the planetary motion. It's because of the energies, but not because of necessarily the planetary motion. So this provided a puzzle of the atom. Protons and electrons are attracted to each other because of opposite charges. So what would you expect to happen? You got an electron and a proton. What are they going to do? Attract. So you'd expect the atom to smash, implode. Rutherford had a real problem with this. Rutherford was like, how could it be in a circle? I mean, it's going to go in, and it's going to either explode, but then you've got all the protons in the nucleus, which means it's going to explode. So it's a constant battle of, is it imploding or exploding? Well, neither. Neither is happening, so what's going on? So we got a little bit of a problem. Yeah, maybe both are simultaneously at the right time, but who knows? We're trying to figure that out. Now, electrically charged particles moving in a curved path give off energy. So if they went around like this, they give off energy. Despite these facts, atoms don't collapse. You would expect them to collapse because they can't continue to move around. Investigations into the nature of light provide the answer. Light provides the answer. How the light is emitted also provides the answer to the question. So, the study of light, the nature of light, is important for the study of chemistry. To understand light, we need to understand the electron volt. This is a unit of energy equal to approximately 1.6 times 10 to the negative 19th joules. It's equal to the amount of kinetic energy gained by a single unbound electron, one electron, when it accelerates through an electric potential difference of 1 volt. So when it passes through, it gains that much energy. It's widely used in atomic and nuclear physics to measure energies of the atom. 1 electron volt per atom is equal to 96.5 kilojoules per mole. This is a pretty common number used whenever you're calculating electron volts per atom. With the electron volts, the energy that is related to those atoms, Michael Faraday, as you know, saw that light and magnetism were somehow related to one another. Maxwell said light is an electromagnetic wave of energy. However, there is a diffraction of particle and waves that shows some different properties. One, if a light behaves like a wave, it curves around a barrier like this. If light behaves like a particle, it would go in a straight line like this. Maxwell thought that electromagnetic energy, electromagnetic waves are light. However, the question is, if you had a barrier and you had a light shining at you, and you were standing over here, would you see it curve around that barrier? Or would it go straight through? What would you see? Do I see the person around there by light curving around you? So, gives us a little bit of a puzzle. Does light behave like a particle, or does it behave like a wave? So, the interesting thing is, when light travels through and around a barrier, it comes out as a curve. And these two curves, if you have two barriers, we'll see if I can't do it. With two holes, they interfere with one another, and the wave it adds up. With several waves, you can see an interference pattern that occurs right here between the two curves interacting. So you see larger waves occurring with the transport of the waves through a barrier. This is a light wave, yes. Okay. This here is an animation. Let me see if I can get this to work right now, of wave interference. So you've got a point source here and a point source here. You can see that as they interact, not only does it make you hypnotized, but there is an interaction called interference between these two waves. So here's another one. Here's a spherical object. When light hits this spherical object, the wave here, you can see the wave spreads out, this one, and the wave over here spreads out. But then they interfere, and you can see that it's actually brighter in this region than it was originally. It's really cool. Why is that? Now, it has to do with light. Okay? The intensity distribution of diffracted light. Okay? When light is diffracted, okay, the intensity, again, increases because as you add the wave amplitudes together, as they collide with each other, they double up. This is something that happens in Newport Beach with a liquid wave called the wedge. What happens is there's diffraction. Two waves are colliding at the same time right on the beach. And bodyboarders go there, and when the surf is 10 feet somewhere else, it's 20 feet there. Quite scary to watch someone bodyboard the wedge. They have a lifeguard on duty all the time, and they also often usually have to take people to the hospital because they land not only they not only are in a 10-foot wave, but the water or 20-foot wave, but the water level is probably about 2 or 3 feet before they hit the sand. It's a pretty cool thing to watch.
I saw the video of the 90-foot wave.
You saw the 90-foot wave? Cool.
Yeah,
Was it?
What was it like?
That would be awesome.
It's most viewed. It's second most viewed as of like 1 o'clock in the morning.
Nice. Nice. Our YouTube expert got us carried on. Yes, sir.
Oh, I was just gonna ask if they had lifeguards there, like creating.
If they had what?
Lifeguards at the beach creating.
You know, I don't believe at the, I don't believe there they do. However, if it's a big storm, they do sometimes send one lifeguard at that location. Yeah, it's a pretty dangerous location for sure when the waves are big. Now, the fact that light diffracts, we'll look at what happens when it diffracts, says that light is a wave. However, the photoelectric effect, there was an observation about this done by, I don't know who, that guy up there. Electrons can be ejected from some metals when they're exposed to light. So you add light to a metal surface, and electrons are emitted, okay, from that surface. The reason why is you add enough light energy that causes the electrons to be ejected from that metal surface, and if you have like another piece of metal for them to go to, they can travel around. As you increase the intensity of the light beams, it increases the number of photons in the light beam, and thus increases the number of electrons emitted. So the more intense the light is, the more electrons can be emitted. Okay? So this principle is the electrons are floating around freely in the metal. The energy is enough to get them excited and excited enough to leave this state, and they leave the surface of this material. Usually they're conducted through something else, but that's how you can get an electrical current by using just light. Now, but this does not increase the energy that each electron possesses. So even though more electrons are emitted, it doesn't increase the energy that those electrons are traveling with. The third observation of the photoelectric effect is if you increase the intensity of the light while keeping the frequency the same, this increases the number of electrons ejected but does not change the threshold value. Okay, so it gives you more electrons being ejected but doesn't change the threshold value. Now, the energy threshold value, as you increase the frequency, the number of electrons ejected here, okay, if you have enough energy being added because the frequency is going up, once it passes this energy threshold, the higher intensity light will just have more electrons than the lower intensity light. Yes?
What is the threshold value exactly?
The exact number, I don't know offhand. For each material, the amount of energy, the frequency is related to energy, so the amount of energy to cause the electrons to be emitted. So there's always, for every material, there's a threshold. When you get past that energy, then the electrons are emitted. Depending on which light you use, you get more or less electrons. So this is a simplification of them. High intensity, low intensity. But here, there's no electrons being emitted until you reach this point, and then, bam. So it doesn't matter if you have a bright light or a dim light. If you have the wrong frequency, nothing's going to happen, nothing's going to happen, nothing's going to happen. Bam, electrons come out. High intensity, more electrons, low intensity, less. But the threshold doesn't change. It doesn't change when it happens. It always happens at the same frequency for the material. Yes? Correct. Intensity means how bright the light is.
It doesn't affect the frequency at all.
Doesn't affect the frequency at all. Very good. Absolutely. Okay? Now, the energy function is a work function. I mean, energy threshold is a work function because you're causing the electron to travel over a distance. So this causes a little bit of a problem. You're moving this electron. So is light a wave or a particle? Diffraction says light is a wave. Photoelectric effect says light is a particle. Which is it? Albert Einstein said both. Now, good job if you thought both. That monkey didn't like it though. The work function. All right, the minimum energy needed to remove an electron from a solid to a point immediately outside the solid surface. So that's that threshold idea. So phi equals Planck's constant times nu. The frequency times Planck's constant gives us the amount of energy for this to occur. Come on, work. Now, this value is usually measured in electron volts. This value exists because light is behaving as a particle. Now, some people say, well, light chooses what it wants to do. Nope, not possible. Can't just choose to be a particle or choose to be a wave one time. It has a duality. Behaves like both. It's not completely understood why it behaves the way it does, although we are trying to explain it using these theories. Now, Einstein's explanation. Okay? Light can behave as both a wave and a particle, and energy is quantized the same either way. So the energy works for both, whether it's a wave or a particle. Electromagnetic radiation is quantized in particles called photons, not quantas. And these photons of light act like a particle and they act like a wave. Kind of hard to imagine both at the same time because there's different properties of each. But that's how Einstein explained it. Photons. Energy of a photon is equal to Planck's constant times the frequency. E equals h nu. Combine this with E equals mc squared. Planck and Einstein's equations stuck together, you get the apparent mass of a photon. The apparent mass of a photon is equal to Planck's constant divided by the speed of light times the wavelength of light. That gives us the apparent mass of a photon. Light simultaneously possesses the characteristics of both waves and particles. So if you combine it, that it has mass and it has energy, and they're related by Einstein's equation, we have some amazing characteristics that some people completely don't understand, and that's okay. Yes, sir?
But like you said, it's apparent mass, but a photon actually has no mass. It's only because of the speed of light.
Correct. Yeah, so this equation, okay, c is the speed of light squared. So if you have a mass that's going the speed of light, it has a certain amount of energy. So what Einstein said was, if it's going this fast, the energy equals h nu. Energy of a wave is h times nu, right? So that means it has to be acting like a wave. If the energies are equal, then it could be acting like a mass as well, but it must be traveling at the speed of light for this to be occurring. So if it's slowed down somehow, it's characteristic properties might be different. Now, not to make it even worse, but the speed of light in a vacuum is supposed to be a constant, right? There's been some experiments that have shown some different results. So, I'm not gonna go there with this. It totally throws a wrench in everything, but it's really crazy. So, we're not gonna go there. Right now, we're just gonna think about the duality of light, which is not something that a chemist can completely understand without a lot of physics. So, we're going to start with the idea that light can behave like a photon, like a wave, and like a particle. Now, after Einstein, Mr. de Broglie from France published a hypothesis. His hypothesis was that any moving particle or object has an associated wave. Whoa. So not just light has a wave-particle duality, but so does the softball you threw at your head. Or the marker that is going to travel through the air and hit you on the head if you keep talking. Both of them have a wave and a particle duality. Yeah. Oh, you like his mustache? I know, it's nice. He founded wave mechanics. All moving particles have a wave-like component. So your mouth that's moving right now has a wave-like component. This is called the wave-particle duality. It's based on a momentum equation. P equals m times velocity, not new. According to de Broglie, any particle with momentum has a tiny wave-like component. And if the particle has less mass, it's going to have a larger wavelength component, vice versa. This is his equation called the de Broglie wavelength equation. The wavelength is equal to Planck's constant divided by the mass times the velocity, which is just momentum. So we should be able to use de Broglie's equation. Yeah, he's French. I married a French woman. I still can't speak French. So, the de Broglie wavelength of an object is this equation here. Now, this is one of the wonderful equations where mass has to be in what? Kilograms. So, the cool thing is, the derivation, where did he get this from? Yes?
The V in the wavelength thing, is that velocity?
Yes. This one is velocity here. How are you supposed to know? Let me show you. Okay, it's got a curvy thing here. It's curvy V. Now it's almost like a U. I don't know if I'll show you on the next slide. I think I have a good one. Yeah, so that's velocity. Okay, this one here is straight. Okay, so this here is the frequency. Yeah.
Wait, the bigger a particle gets, the smaller the wavelength?
I'll have to check that. I was thinking about it for a second when I said that. We'll check that in a minute. Yeah.
At the bottom, is that a V or a T? Oh yeah,
This one here?
that's the velocity.
Yeah. All right, now, the derivation of this equation. It's really fun to do, especially if you love math. It's so cool. You got the energy. Okay, energy equals hv, and energy equals mc squared. Wait a minute, we talked about this, right? Combine the two together. So, if E equals E, and that happens at the speed of light, then you plug this in. mc hc over lambda equals mc squared. H over the lambda equals mc. M is the apparent mass of an electron with speed of c. The speed of light relates to the de Broglie wavelength here, where c is replaced by the velocity of the object. So if it's traveling at the speed of light, okay, this here, this velocity would have been c, but if it's not traveling at the speed of light, it is